Okay. This is the last class for chapter 9, Diagonalization. So diagonal matrix is a matrix whose off-diagonal elements are all vanishing. So distinct from general matrix, diagonal matrix has a very simple algebraic structure. Suppose that we have dA, whose diagonal elements are this, and dB, whose diagonal elements are BI. And if I multiply two diagonal matrices, what I find is just a multiplication of row and column to find the ij element. This shows that only a single element in a single column and only a single element in a single row survives. Non-vanishing contribution comes only from the direct product of A1 and B1, A2, B2, and AN, BN. Because these product of two numbers are commutative, the diagonal matrix product dA dB must be the same as dB dA. In the same manner, we can generalize this to find the powers of diagonal matrix is each element becomes a power of its own element, and still the off-diagonal elements are all vanishing. Because of this, if we exponentiate the diagonal matrix, it is a summation of 1 over k factorial diagonal matrix power. And if I apply this to here, we have summation is similar for every element separately. And we know that this is the exponential of the first element and the exponential of the last element. In addition, the determinant of this exponentiated diagonal matrix is just a product of these diagonal elements. Product of these diagonal elements is just the numbers. So I can apply the law of exponent. So just addition of exponent. If I add all these exponent, because dA is A1 to AN, the sum of these all elements is just a trace of dA. Therefore, it becomes trace dA. Suppose that this diagonal element is traceless. That means the sum of all the diagonal elements vanishes. Then it becomes if trace dA equals 0, then determinant of exponential dA equals 1. Because e to the 0th power, this trace of diagonal element vanishes, then it is exponential 0. This is exponential 0. That is determinant equals 1. In a similar manner, the cosine of the diagonal matrix and sine of diagonal matrix can be computed in a very easily. As we can see, the powers of the diagonal matrix is to replace the element's power. And if I sum all contributions all together, each elements are to be summed separately. And this is cosine. So each element has a cosine of the original matrix. in a similar manner, sine can be computed in a similar way, and sine of diagonal matrix is just sines of diagonal elements. All right. Next, we consider the similarity transformation. Consider there are two matrices. We use a similar. Similar matrix is connected. There is some relationship that they are related in this way. Matrix is multiplied to some matrix. Inverted matrix lambda is multiplied and its inverse is multiplied to the backward, and this resultant matrix is called similar to the original matrix A. For example, let us consider A and B. And here the lambda is given like this. So lambda is here, and the inverse of lambda is given like this. Let's check if it is true. Lambda is here, copy it, lambda inverse. If I multiply two matrices, I obtain diagonal elements, and this one 1 minus 1 vanishes, 0 0 vanishes. So it is an identity. So if the product is identity, this one is inverse. Okay, let's compute the lambda A, lambda inverse. Let's see if it is true, if it is equal to B. Lambda is here, and lambda inverse is here. I copied A. If I multiply this, I have 1, this is 1, 0, and 0. Multiplication of this and this will give 1, 1, and 1, 1, 1, 1, 1, 1. This is the same as B. So the B is expressed as the product lambda A, lambda inverse. Therefore, we say B is similar to A. Okay. Let us consider the trace of A. Trace of A is 2 plus 0 is 2. What is trace of B? This is 1 plus 1 equals 2. The trace A and trace B are the same. And actually, under the similarity transformation, trace is conserved. We will prove this later. What's the determinant? Determinant of A is 0 minus 0, 0. Determinant of B is 1 minus 1, 0. Determinant of A equals determinant B. So under the similarity transformation, determinant is also preserved. And actually the eigenvalues are also preserved. Let's see what happens to the eigenvalues and eigenvectors. So circular equation for matrix A is matrix A is here. I copy the matrix A and subtract the lambdas in the diagonal elements and take the determinant. Determinant is 2 minus lambda times minus lambda. So the eigenvalues are either 0 or 2. So if I substitute 0 here, 2, 1, AB is the eigenvector. And the next one is 0, 0. The first contribution shows that, first element shows that 2A plus B equals 0. So I can choose 1 and minus 2. And if I normalize this in a correct way, it is a 1 square root of 5, 1 minus 2. I have eigenvalue 2. If I substitute in here, what I obtain is 2, 0, 1, and 0 minus 2. If I substitute eigenvector, the result shows that regardless of value of A, B must vanish. Therefore, the eigenvector for this is 1, 0. We notice that these two eigenvectors are not orthogonal. The reason is that A is not a Hermitian matrix. We will show that this is a Hermitian matrix. Hermitian matrix eigenvectors of Hermitian matrices are orthogonal. All right. So anyway, the similarity transformation preserved the eigenvalues for the matrix A and matrix B. The eigenvalues are 0, 2, and let's see what happens to the case of B. B is this here. The circular equation, subtract lambdas in the diagonal element. Determinant is 1 minus lambda squared minus 1. Factorized, I also have lambda equals 0 or 2. For lambda equals 0, substitute lambda in here. Lambda equals 0 here. Then 1, 1, 1, 1. Eigenvector AB should be 0. So A plus B equals 0. So I can choose minus 1 and 1. And normalized eigenvector should be 1 over square root of 2, this one. If I substitute lambda equals 2, it is minus 1, 1. The relation we obtain is minus A plus B equals 0. So they are the same. So 1, 1. Normalized one should be this one. I find that psi lambda equals 0, dagger, psi lambda equals 0 is 1 over 2, minus 1, 1, minus 1, 1. This is 1 over 2, 2, so 1. Okay. Psi lambda equals 2, dagger, psi lambda equals 0, 1 half, 1, 1, 1, 1, 1 half, 2, 1. Dagger lambda equals 2, 0, lambda equals 2 equals 1 half, 0, minus 1, 1, 1, 1, 0. Dagger lambda equals 2, psi lambda equals 0, 1 half, 1, 1, minus 1, 1, 0. Therefore, delta ij. In addition, okay, that's it. Next. All right. So, in summary, A is a n by n matrix. Lambda is an n by n invertible matrix. Lambda transforms a column vector X as in this way, just like the rotation matrix multiplied to the Cartesian vector. So from this, we find that X equals lambda inverse X prime, because I can multiply lambda inverse in both sides, that the inverse transformation is just lambda inverse. So lambda, because lambda transforms a vector in this form by multiplying lambda to that vector, we notice that A times X is a vector because A is a square matrix and X is a column matrix. So column vector. This column vector is multiplied, then this one behaves like X. Therefore, this one transforms into lambda AX. We substitute x equals lambda inverse x prime. That means AX transforms into lambda A and lambda inverse x prime. Thus, AX transforms into A prime x prime, where A prime should be lambda A lambda inverse. Okay, so transformation rule for the column vector is to multiply lambda, and a matrix is transformed into lambda A lambda inverse. So this is just like the rotational transformation of a rank to Cartesian tensor. We say A prime is a matrix similar to A, and lambda, the invertible matrix lambda, is the similarity transformation. This similarity transformation keeps the dimension, so that, for example, this may be the eigenvector of A matrix, A or either A or A prime, and if it is the case, the other one will be like that in case A is Hermitian, but we will see in the next page. And another example is we have orthogonal eigenvectors in this form. So anyway, they are orthogonal as long as A is a Hermitian matrix. The similarity transformation preserves many things. First of all, determinant is preserved. Let us see determinant of the matrix A prime that is similar to A can be expressed as the determinant of lambda A lambda inverse. We know that determinant of a product is a product of determinants. So if I make use of this repeatedly, product of the three matrices is just determinant lambda, determinant A, determinant lambda inverse. We know that the determinant of inverse is a reciprocal of the determinant. Therefore, these two factors cancel. And this is the original determinant. So any similarity transformation does not change the determinant. Next, trace. Trace of a product, the product of two matrices, A times B, is a summation over I, the diagonal elements. The product AB should be computed as Aij, Bji summed over J. In a similar manner, I can compute the trace of BA. Trace BA is the BA's diagonal element summation. And if I expand this, it is a BJI and AIJ summed over I and J. Now, these are just real or complex numbers. They are commutative. So move this one to the left hand side. We see that the trace of AB and trace of BA are identical to each other. Let us consider the similarity transforms, similar matrix. Trace of similar matrix should be expressed as a trace of lambda A lambda inverse. And because this is a product of lambda and A lambda inverse, we can exchange the order of the multiplication because it's trace. So move this one to the left and right, then lambda inverse lambda is combined to have identity Therefore, it is the trace of A. So under similarity transformation, trace of a matrix is invariant. In addition, we have an interesting result. Eigenvalue is also preserved. Consider an eigenvalue equation Ax equals lambda x, where A is a n by n square matrix, complex square matrix, and x is an eigenvector. If I multiply an invertible matrix lambda to the left-hand side and insert identity and replace it by lambda inverse lambda, then what I obtain on the left-hand side is the lambda A lambda inverse. That is the A prime after the similarity transformation lambda. And right-hand side has lambda, small lambda, this number, this eigenvalue is still there, and lambda x is the new vector obtained after the similarity transformation. So if I replace all the vectors and matrices in terms of the similarity after the similarity transformation, we have A prime x prime equals lambda x prime. Thus, under this similarity transformation, the vector is transformed in a systematic way. Matrix is also transformed in a similar satisfying this rule, but the eigenvalue is remaining the same. So the eigenvalue is invariant. Because the eigenvalue is invariant, the algebraic multiplicities are also invariant. I mean, if A has eigenvalues lambda equals 0, double, lambda equals 1, single, so this is a 3 by 3 matrix. So A prime has a still lambda equals 0, double, and lambda equals 1, single. Okay, multiplicity is also preserved under the similarity transformation. All right, wait a second. So let us consider the eigenvectors and eigenvalues for a Hermitian matrix. We are only interested in the Hermitian matrices from now. Then, as we already have proved, any Hermitian matrix has the real eigenvalues. All the eigenvalues are real, and eigenvectors are orthogonal. And after normalization, we can always find the completeness relation. That means all of the eigenvectors, the circular equation states that there are n, and if the Hermitian matrix A is n by n, there are n independent basis vectors. They are called eigenvectors. Oh, let us say the xi, xj are eigenvectors, and we can normalize to be unity so that their projection using scalar product, this scalar product is xi dagger xj should be canonical delta ij. Therefore, we are interested in this kind of situation. Suppose that we have a matrix lambda, and lambda is just list of row vectors, and those row vectors are eigenvectors. If it is the case, the lambda dagger should be just all the rows are flipped into columns and multiplied by the transformation of a complex conjugate. So lambda times lambda dagger's ij element should be the first one's ith row, that is xi. Ith row is xi. And multiplied by the jth row, that is xj. Xi dagger multiplied by xj will be lambda dagger's ij element. And this is because of this orthogonality relation for the eigenvectors of Emission matrix. This is chronic delta. Therefore, the ij element is chronic delta, then the matrix identity matrix. The left hand side is a lambda dagger. That means if I construct the matrix lambda with the Hermitian conjugate of n eigenvectors to be the rows of this matrix in order, then lambda must be unitary. Lambda dagger should be lambda inverse. Lambda is a unitary matrix. This is true for the case A is A dagger and X satisfied this eigenvalue equation, right? All right. Next we consider this one. Because this is identity, let us consider the ith column of the right hand side. Because the identity is E1, E2, E3 to En, ith element is EI. Ith column is EI. So let us consider the ith column. If I choose I, this is lambda and multiplied by the ith column of lambda dagger, that means xi. So if I multiply this here, blah blah blah, the first one will vanish and there should be some xi dagger. This multiplication must be 1, and except that everything else will be 0. So only the ith element is identity and remaining pieces are all 0. Therefore, as we have expected, this is EI. From here, we find that the first eigenvector after being multiplied by lambda, that is this is lambda, the final resultant matrix is E1, and whose matrix element matrix representation is just elementary unit vector, unit column vector 1 0 0 0. This is quite simple, and in such a way, lambda times xi should be EI. Therefore, this one means our eigenvectors are trivial column vectors. And in that case, eigenvalue equation states that elementary matrices multiplied to a matrix, some matrix, it gives some number, that eigenvalue. That means in this space, after this similarity transformation, A is diagonalized to be the eigenvalue. off-diagonal elements must vanish. Everything must vanish because the eigenvectors are just a simple elementary matrices. So this is a way how to diagonalize a Hermitian matrix. So, in summary, we have xi's column vectors in general for the eigenvectors. And these eigenvectors are, we take the Hermitian conjugate of these eigenvectors and put the rows to construct the similarity transformation matrix lambda. In that case, lambda dagger should be just column vectors composed of x1 first, second, and third, and each column is the eigenvector of that matrix. After rotation, x becomes lambda x, xi becomes lambda x, and that is just ei. Ei is the trivial elementary column vector, where ith element is unity, and except that element, everything else is vanishing. This transformation gives A transformed into lambda, A, lambda dagger, and because eigenvalues are preserved, all of the elements in the diagonal elements in this space should be in this form. That is written in here. This is the result of diagonalization of the Hermitian matrix A. In our analysis, we mainly consider similarity transformation lambda, which is unitary. Unitary means dagger is inverse. Actually, dagger, Hermitian dagger, should be understood as a transpose matrix complex conjugate, or complex conjugate matrix of transpose. Okay, if it is real, we can ignore this complex conjugate, then lambda dagger should be understood as a lambda transpose, and if the inverse is equal to lambda transpose, then lambda is an orthogonal matrix. That is for the rotational transformation. Okay, suppose that ij element is lambda ij. Transposed matrix ij element is lambda ji element. Complex conjugate matrix ij element is just lambda ij elements complex conjugate. A Hermitian conjugate ij element should be transpose ij element complex conjugate, because it's transpose lambda ji is complex conjugate, so we can write it lambda ji complex conjugate. So anyway, if it is lambda dagger, lambda equals identity, lambda inverse is lambda dagger, and we say lambda is unitary. So this is a very important result. First, transformation diagonal. In order to diagonalize a Hermitian matrix, we first find out solve the eigenvalue problem. By solving the eigenvalue problems, you find eigenvalues and eigenvectors, and you normalize the eigenvectors in this way, including multiplicity. As soon as you find the normalized eigenvectors, you list up the x daggers as a row vectors, list from first to the end. This is the transformation matrix lambda that diagonalizes the matrix. The matrix X transforms into lambda X, and matrix A transforms into lambda A lambda dagger, because lambda is unitary. Lambda dagger is just, if you take the Hermitian conjugate of this, you will find that this is x1 to xn. Alright, it is trivial to show that lambda lambda dagger equals identity. Because x transforms into this, and we find that lambda xi transforms into lambda I, and that is the trivial column vector, unit column vector. By making use of this, we check the completeness relation. First, let us consider this identity. If I take the complex conjugate and transpose, then the Hermitian conjugate of this equation, we find this is flipped and Hermitian conjugate is put. So xi dagger, lambda dagger equals ei dagger. Because trivial unit matrix, unit column vector is real, it is the same as a transpose. The complex conjugate doesn't affect the result. Using this column vector and using this row vector, multiply directly, okay? multiply this one and this one directly. The right hand side is multiply this ei and ei dagger directly. You will find that this is just identity. We know E1 times E1 equals E1 dagger 1 0 1 0. That is 1 0 0 0. In the case of 3-dimension, for example, E2 times E2 dagger this is 0 0 0 0 1 0 0 0 0, and E3 times E3 dagger 0 0 1 cross 0 0 1, that is 0 0 0 0 0 0 0 0 1. If I sum everything up, EI cross EI dagger should be 1 1 1. This is true for any arbitrary number of cases. So this is completeness relation. The right hand side is completeness relation. Left hand side, here. So let us multiply lambda dagger from the left and lambda from the right. Then this one will disappear and this one will disappear, and lambda dagger is multiplied to identity and lambda is multiplied to the identity on the right. But because this one is lambda and lambda dagger lambda, and we know that this is a unitary matrix, so eventually it becomes identity. Therefore, even in the previous, before the diagonalization, eigenvectors, a direct product of eigenvectors summed over all states is identity. This is a proof of completeness relation regardless of any coordinate system. So that are related through the unitary transformation. Let us consider simple example, very simple example, sigma 3. Sigma 3, Pauli sigma matrix, sigma 3 equals 1 minus 1, 0, 0, right? So first, let us find out the eigenvalue and corresponding eigenvectors. Sigma 3 minus lambda identity determinant must vanish. So this is equivalent equation. So minus lambda minus 1 minus lambda determinant. This one should be lambda minus 1 lambda plus 1. Therefore we have eigenvalues either plus 1 or minus 1. Convention is to put the plus 1 first and minus 1 next. Substitute lambda equals 1 in this equation. It is 1, so 0, 0, 1, 0 minus 2. Suppose this trial solution for the eigenvectors AB. The first equation gives just 0. The second equation shows the minus 2b. That they all both must be 0. This one shows that b must be 0. Then I can choose this one 1, 0 to be the eigenvector corresponding to the eigenvalue lambda equals 1. Next one, I have eigenvalue minus 1. Substitute this one is this eigenvalue problem. We have 2, 0, 0, 0. And trial eigenvector. If I multiply this, it is a 2a, 0. Should be 0, 0. Therefore, a is 0. Therefore, the eigenvector corresponding to the eigenvalue minus 1 should be 0, 1. This is actually the spinner. We usually write as a spinner C, up, spinner down. Although the eigenvalues are plus minus 1, then actual eigenvalue for the SG should be plus minus 1/2 h bar. So this one indicates this one, and the spin matrix, Pauli spin matrix is h bar over 2 sigma. So 1/2 h bar is removed in this calculation. Alright, I have eigenvector with eigenvalue plus 1 is 1, 0. Eigenvector with eigenvalue minus 1 is a 0, 1. First, if I check the normalization, 1, 0, 1, 0 is this 1. 1, 2, 1, its dagger is this one. 1, 2, I mean the 1 is for lambda equals 1, 2 represents the case for lambda equals minus 1. So that is a 0, 1, vanishing. 2, 1, 2's dagger, and 1 is here, is vanishing. And 2, 2, 2, 2, this is 0, 1, 0, 1, there's 1. Therefore, it satisfies the orthonormal relation. As soon as the eigenvector satisfies the orthonormal relation, then we can check the completeness relation. Direct product of 1 and 1 is 1, 0, 0, 0. This is 0, 0, multiply 1, 0, 8, 1. So if I sum these two matrices, this is identity. So it reproduces the completeness relation. So this is complete set of the eigenvectors, and this two eigenvectors spans the Hilbert space for spinner. Okay, more general case. In general, Pauli matrices are similar. What we just have found is the eigenvectors and eigenvalues for sigma 3. And first of all, we notice that the traces of these three matrices are all 0. Trace is 0 plus 0 is 0, 0 plus 0 is 0, and 1 minus 1 is 0. All three matrices has the same trace. Again, determinant 0 minus 1. Okay, minus 1. 0 minus 1. Minus 1. Minus 1, 0. So minus 1. All three matrices has determinant minus 1. They are quite interesting. Again, all three matrices are Hermitian. All three matrices are Hermitian. Sigma 1, sigma 1 transpose, sigma 1 transpose complex conjugate. This is sigma 1. So sigma 1 dagger is a sigma 1. Sigma 2 minus I 0. Sigma 2 transpose. Sigma 2 transpose complex conjugate. It is sigma 2. Therefore, sigma 2 dagger is a sigma 2. Sigma 3 transpose itself, sigma 3 transpose complex conjugate itself. Therefore, sigma 3. Therefore, for all I, sigma I dagger is a sigma I. This is sigma I is traceless and Hermitian. Right? So consider sigma 3. What we just have obtained is the eigenvectors are 1, 0, 0, 1. And sigma 3 has the diagonal form. It's a diagonal form. Alright. The first element is the eigenvalue lambda equals plus 1. This element, 2 element, is the eigenvalue. Alright. I know that this one, because of these relations, and these are Hermitian matrices, I expect that they must be related by a similarity transformation. As you know, any Hermitian matrix, this is a Hermitian matrix, any Hermitian matrices are diagonalizable. And the trace and determinant are the same. I suspect that the three matrices has identical eigenvalues, and they are related by a similarity transformation. What I want to do is to find out the similarity transformation to connect all those three matrices. First, let us consider sigma 1. Sigma 1, we compute the sigma 1's eigenvalue equation. Sigma 1 is 1, 1. So subtract by minus lambda in the diagonal element. And this determinant should be lambda squared minus 1. And again, I find that identical eigenvalues are provided. So they must be similar. And here we have plus 1, substitute in the eigenvalue equation, and trial eigenvalue, eigenvector. And this one shows that minus a plus b equals 0. So they must be equal. So I can choose 1, 1, for example. But if I want to normalize it to unity, I multiply 1 over square root of 2. So this is the correct normalization for this lambda equals plus 1 case. For lambda equals minus 1 case, it is 1, 1, 1, 1 multiplied by trial eigenvector that gives the opposite sign for A and B. Therefore, I can simply choose minus 1, 1, 1 over square root of 2 for the normalized eigenvector. So that means a spin-up state for along the x-axis, spin-down state for along the x-axis. Now, because we are equipped with any diagonalizing the matrix, what we have is just the two eigenvectors. The unitary transformation matrix to diagonalize this matrix must be side 1 dagger, side 2 dagger in correct rows. So you take the Emission conjugate, we have factor of 1 over square root of 2, and this 1, 1 appears in the first row. The second eigenvector is transformed into the Emission conjugate, that is a minus 1 and 1. So we already proved that this lambda is a unitary matrix. So inverse is just Emission conjugate. Emission conjugate is simple. Transpose and take the complex conjugate. But this is a real matrix, so transpose is sufficient. We expect that this result should be, it must be sigma 3. Let's see. Lambda is here. Sigma 1 is a 1, 1, off diagonal 1, 1, and lambda dagger. We have pulled out 1 over square root of 2 twice in front of the multiplication of the last two matrices will give this one. This one gives 1. This one multiplied to second row 1, and this is 1, and then multiply this one to this row, we have minus 1. Now we compute this one to here 2, this one to here 0, this one to here 0, and this one to here we have minus 2. Now 2 to cancel to find that this diagonal elements 1 minus 1 0 0. This is exactly the same as a sigma 3 Pauli spin matrix sigma 3, and this plus 1 and minus 1 is exactly the same as what we have obtained for the eigenvalues. This is not the end. We can also consider in summary, what we have found for the eigenvectors for the sigma 1, they are already complicated, mixed state. The coordinates are good, but this coordinates useful for the quantization along the z-axis. That's the reason why if I quantize along the x-axis, the spin up and down structure is mixed for the, because this is the 1 0 is the spin up state for sigma 3, the z-axis. But what we are working on is regarding the spin quantization axis, x-axis. So x-axis spin along the x-axis has either spin up and down if we measure the spin along the z-axis, something like that. All right, so we have normalized the states for the eigenkets, and we can reproduce this direct product to be the identity. Okay, this one can be tracked. Great. Psi 1, psi 2, cross 1 dagger, psi 2, if I add these two, it must be identity, right? But as we know, this sum gives correct. Okay? And we have eigenvalues is invariant, the diagonal element after diagonalizing matrix by making use of the similarity transformation lambda. What we find is a sigma 3. Next we consider the case of sigma 2. If we consider the case of sigma 2, similar calculation is being carried out. Let me just consider the case. Okay, lambda equals plus 1, so minus 1 minus I, and AB is the trial eigenvector. So multiplication gives this kind of relation. Substitute A equals 1, then B equals I. So 1I style. We know the normalization should be 1 over square root of 2. And for minus 1, we have normalization. We have the eigenvector, orthogonal eigenvector, to be I1 in a similar manner. All right, we have a first eigenvector for plus 1 and minus 1 in such a way. The similarity transformation that diagonalized the matrix must be the first one dagger as a row, second one dagger as a row. So first one is this one, its dagger is 1 over square root of 2, and 1 instead of I we have minus I. Second one dagger is 1 over square root of 2 minus I and I in here. And because inverse is dagger, the lambda dagger is, what's that? Transpose is the same, but after the transpose we have to take the complex conjugate. The lambda dagger, that is the lambda inverse, should be of this form. Combining this lambda and lambda dagger to diagonalize sigma 2, we have lambda here, the square root, 1 over square root of 2 factors appear twice, so we have 1/2. This matrix and this Pauli sigma matrix sigma 2, and then inverse. At the end of the day, after all the calculation, we find this is exactly the same as sigma 2 as we have sigma 3 as we have expected. This is what we just have found for checking the unitarity of the matrix explicitly in the past, because we have made the general proof already. So what happens to sigma 2 under the similarity transformation? This is what does for sigma 1. This is sigma 1. Sigma 1 becomes sigma 3 after diagonalization. Sigma 2 also becomes the sigma 3 after diagonalization. All right. So next we consider the exponentiation. What are the benefits of diagonalization? It is very good for the exponentiated matrices. First of all, matrix representation after diagonalization. So psi 1 is actually E1, E2, and En. And they are all real, even though the matrix A is complex Hermitian matrix. So this simple matrix representation is the first reason why we consider the diagonalization. The second one, after diagonalization, elements are all vanishing, off-diagonal elements are all vanishing, and the only surviving pieces are diagonal elements. If it is the case, exponential of this matrix is trivial, because everything will be exponentiated separately. What happens to the case e to the alpha A, where A is a Hermitian matrix, A is a Hermitian, and alpha is an arbitrary complex number. All right, so we have alpha A, but if A is a Hermitian, A is always diagonalizable, right? Therefore, this exponential can be expanded in such a way after expansion, because A is diagonalizable in such a way, we substitute this one. A should be A lambda inverse diagonalized matrix lambda. If I multiply this one repeatedly, the left-hand side, right-hand side, lambda and lambda inverse are cancelled exactly. The only surviving lambda dependence appears at the end, and in the middle we have diagonal matrix power. We already studied that diagonalized matrix has a simple power, and it is trivially exponentiated in such a way where the diagonal matrix has eigenvalues in here. All right. So, for example, we consider Pauli sigma matrices to simplify the calculation for the spinor rotation. This is a simple example. We could have considered the rotation of a three-dimensional object, but the matrix representation is too big, so this the rotation matrix for this Pauli spinors using this exponentiated Pauli sigma matrix is much more compact. All right, first consider the Clifford algebra. Any Pauli sigma matrix product is either identity or the Pauli sigma matrix. It's very, very important, right? First, sigma 1 squared, you can make an explicit calculation to find that it is an identity matrix. Sigma 2 squared, it is also the identity matrix. Sigma 3 squared is also the identity matrix. If I multiply different indices, those sigma 1 times sigma 2, the final result is I times sigma 3. And this permutation should be considered. If I exchange the order sigma 2, sigma 1, then your result will be minus I sigma 3. That's the reason why we have I epsilon ijk Leibniz-Civita tensor multiplied by sigma k. Therefore, sigma 2, sigma 3 is I sigma 1, sigma 3, sigma 2 is minus I sigma 1. Sigma 3, sigma 1 is I sigma 2, sigma 1, sigma 3 equals minus I sigma 2. Therefore, this one is true. This one can be used to sum these exponentiate Pauli sigma matrices. Next, if I apply this Clifford algebra, this A dot sigma times B dot sigma should be AI, BJ, where here A and B are vectors. These vector components can be pulled out, but sigma matrix should not commute. The order of sigma matrices should not be moved. It should be kept as it is. And we replace this one, this delta ij identity plus I epsilon ijk sigma k. If I sum I and j, it is a scalar product A dot B, and it is a triple scalar product of A cross B dot sigma matrix. So, if we substitute B equals A, this one disappears because there's symmetric and anti-symmetric summation. So, vanishes. Only the A squared identity is surviving. Therefore, in general, A dot sigma is the to an even power gives A squared n power, proportional to the identity. If I have odd numbers, then even powers will give the A squared to n, and we have a single sigma matrix A dot sigma. Sure, linear combination of three sigma matrices. If I compute the exponentiate form of exponential EI A dot sigma, then the expansion can be separated into two pieces, but even powers and odd powers. If I consider the even powers, I can substitute this result. So this one has the proportional to identity matrix. If I have the odd powers, then even powers will appear, and I have a single more sigma dot A appears. I pull out the sigma dot here, but I divide it by magnitude of A vector in order to match the index. There's a 2k plus 1 factorial with the power of magnitude of A vector. Then trivial summation can be made to replace this one with cosine A and this one with sine A. So exponentiated form of this one gives this matrix is just a linear combination of identity and Pauli sigma matrices. Next we consider this one is unitary. Lambda is I sigma dot A. Actually, we can make use of this expression, but in a trivial way, but we can do in a different way. So let me show this. This lambda and lambda dagger is here. Exponential is expanded, and we find that the dagger, Hermitian dagger, is inserted. Then every factor, this is real, the same. I becomes minus I. We have A is a real vector, and sigma is a Hermitian. So sigma vector dagger should be sigma. So the only change is the flip of the sign in front of I. Therefore, this one's dagger is a minus I, A dot sigma. Let us multiply lambda and lambda dagger. Then we find that this is exponential I, A dot sigma, and lambda dagger gives an exponential minus I eta sigma. Summation can be made separately for the dummy index k, 1 over k factorial, I a dot sigma's kth power, and we have a different dummy index L 1 over L factorial minus I a dot sigma's nth power. The summation can be made reorganized in the resummation. So k factorial L factorial is factored out. I has a k plus Lth power. We have minus I Lth power, and then sigma dot a dot sigma has k plus Lth power. We redefine k plus L to be m, and this summation runs from scanning k space L space. K runs from 0 to infinity, and for each k, L goes to 0 to infinity. However, we can make a summation. M goes to 0 to M goes to 1, 2, 3, 4, and change the L in this way. Alright? This summation can be made. So, this is M. So, let us see. M summation is made. So, we have M summation. I have a factor of I. K plus 8 is M. And K is replaced with M minus L. L is still the same, minus L. And this one is replaced with mth power. Okay? And here I have I to the M. Sigma dot A to the mth power is pulled out. However, I can divide this m factorial here and multiply m factorial over there. Alright? But this one, we find this is binomial expansion. Binomial expansion of 1 minus 1 to the mth power. And this one survives. This one is 0 to m. And if it is m is greater than 1, then everything vanishes. But it survives only if m equals 0, that's the initial term. Both the k and l are equals to 0. That is a lambda dagger should be the 1. That means lambda dagger is inverse. So that is this expression. A is a real vector dot Pauli sigma matrix I. This is a unitary matrix. Actually, the unit in general, we can consider this one. This is a real parameter. A is a Hermitian and traceless. And this is I. U dagger, because it's a Hermitian, A dagger is A, minus is flipped. With the same summation rule, we have identity. So U dagger equals U inverse. But I did not apply the fact that A is traceless. Let's see what happens A is traceless. If A is traceless, A is a traceless Hermitian, and alpha is a real, and I is a pure imaginary number, then we find that even the determinant is fixed. Let's see. There exists a similarity transformation, lambda A, lambda dagger. Because the similarity transformation keeps the trace, and we know the trace of A is 0. Okay, traceless. And after diagonalization, matrix A is transformed into this simple form. Let's see. Determinant of U can be computed. And here, this A is, because A is diagonalized into AD, we have this kind of form. And in this exponential expansion, a dagger A survives only at the end. And because we have proved that lambda dagger is inverse, determinant vanishes, only remaining this piece in the diagonalized form. Exponentiated diagonal matrix should be exponentiated eigenvalues. Determinant of this is the product of this, then you find exponential I alpha trace. This is a sum of all of the eigenvalues, This is trace of diagonalized matrix. And trace of diagonalized matrix must be the same as trace of original matrix. But the trace of original matrix 0. So this is 0. If I substitute 0, exponential 0, and exponential 0 is a plus 1. Therefore, this kind of unitary transformation has the determinant plus 1. Alright, so we have completed the diagonalization of chapter 9.